Um, Hi guys, I welcome you once again to the interactive session of the course Fundamentals of Conduction and Radiation. And as you guys are aware, we are in the radiation part of this analysis, and we are, going towards the end of this journey. Maybe we'll have one or two more, sessions after this session, and then we will formally end this course. And as you know, you guys will have your exams, which is the customary thing that typically happens in a typical NPTEL course. Okay. Uh, Anyways, so as you know, our drill is similar. We will start off today by having a recap of what we saw it in the last week. Uh, go through quickly go through like the things we saw, and then we will discuss the agenda for today's discussion. Okay, so in the last week, we learned into something which is known as emission from real surfaces. But before that, we looked into an important perspective of looking into radiation heat transfer, which is known as the band emission. And this band emission was equally true for any objects, be it a black body or be it any real surfaces. The idea was that if we basically want to quantify, so we looked it into we looked it from a mathematical perspective, we looked it from a graphical perspective as well. So as to we plot the spectral emissive power with respect to the wavelength, and what we said is that if we want to quantify how much is is the radiation that is between a certain particular wavelength with corresponding to the entire emission taking place through the entire wavelength, that is through the entire band of wavelength from 0 to infinity. And we quantified that by using a fraction known as f0 to lambda, whose definition is basically the area of this graph corresponding to the particular wavelength that we are trying to see, uh, with respect to the entire band of wavelength that this spectral emissive power encompasses, basically. Okay. And as we know that this particular area is always less than the entire area, so this band emission function happen to be a fraction, and this is what its formal mathematical definition of. We saw this as the formal mathematical definition of this band emission function. Okay, and then we argued that this integral from 0 to infinity, this EB lambda d lambda, which is basically you are integrating the spectral emissive power of a black body from its through the entire band of wavelength, and that basically give rise to the fact that this becomes equal to sigma times the fourth power of its temperature, which is nothing but the Stephen Boltzmann law. And then we argued that this f0 to lambda simply simplified to this integral divided by this sigma times its temperature raised to the power 4. Okay. And as I said, this is the fraction of the emissive power that is in the band from 0 to lambda. And then we discussed that what happens if we want to seek a fraction between any generic wavelength lambda 1 to a generic wavelength lambda 2, where you can interpret that your lambda 2 is greater than lambda 1, or in any other way around. And then we have used the basic principle of integration to write an integral which is from a to b as the integral from 0 to b minus the integral from 0 to a. Okay, so this I think you are aware from your high school mathematics. So we just have used that thing to eventually find out that this f lambda 1 to lambda 2 can be written in terms of its integral from 0 to lambda 2 minus its integral from 0 to lambda 1. Okay, so this is some things, these are some things that we saw related to the band emission function, and we use this concept in order to in order to understand, in order to in order to in a better way kind of understand what is known as the emissivity, and specifically the spectral emissivity, because this is a property that distinguishes your body and a black body, where we define something which is known as the total hemispherical emissivity as the total emissive power of a real body to the total emissive power of a black body, provided these two bodies are at the same temperature. Okay, and then we went on to define something which is known as the spectral emissivity, and these are just some basic step down approaches that we did. So we started off by defining something which is known as the total hemispherical emissivity for real bodies, and then we defined the spectral emissivity, and then went on to define something which is known as the spectral directional emissivity. Okay, and thereafter we looked into a very useful numerical on calculating this total hemispherical emissivity, given that the spectral emissivity varies along the wavelength as shown in this figure. Okay, so by taking use of the concept of this band emission function, we determine this total hemispherical emissivity, started from the very basic definition of this total hemispherical emissivity, and determine what your total hemispherical emissivity would look like. Okay, using the fact that you know the band emission function values, provided you know the product of your wavelength and the corresponding temperature. Okay, so these are the things that we saw in last class, and we ended our discussion with something which is known as the Kirchhoff's law and gray bodies, and we formally define what Kirchhoff's law is actually, and what Kirchhoff's law basically states. And we saw that these form of Kirchhoff's law, which says that your spectral directional emissivity is equal to the spectral directional absorptivity, and these forms the very basic statement of Kirchhoff's law. And as I said, these are just applicable, these form of Kirchhoff's law, to be precise, is always applicable, because these terms, this epsilon lambda theta and alpha lambda theta, these are just inherent surface properties, because we have very pinpointedly specified that these are spectral and directional properties. So we don't have to invoke assumptions like, for instance, like the gray body or diffuse surfaces and things like that. Okay, so these form the very basic form of this Kirchhoff law. And then we argued that if I now have a diffuse body, I can simply write that I can remove these directional dependencies, and same thing goes for the case of a gray body, where I can remove the lambda dependencies. Okay, so for instance, I can write that my epsilon is equal to alpha only when I have a diffuse and a gray body, and then in that case these dependencies on this the wavelength and the direction don't come into the picture. But if we want to have a general statement of a Kirchhoff law, I would always suggest you to basically state this as the most general statement, because this is always true and it's an inherent property of the surface. But having said that, if we invoke the assumption of a diffuse and a gray body, I can simply write that my epsilon is always equal to alpha, corresponding to a particular temperature for a diffuse and a gray body. Okay, so these are some things that we saw in in the last class. Before formally going into the discussions of this week, where we will look something which is known. So I'll state all these things what we are going to see today. But before that, if you have any doubts, I'll stop here for a couple of minutes. If you have any doubts or any suggestions, and if you want to speak it out, or if you want to have a discussion on it, please feel free to let me know on these aspects. Okay. Yeah. In the meanwhile, I'll just check if I started the recording or not. Okay, the recording is in progress. All right, guys. If no questions, so today we'll be discussing another important, you can say, a perspective of radiation heat transfer, and this is typically known it's typically known in the literature as view factors. People also sometimes call it the shape factors, or they also sometimes call it as the configuration factor as well. But most commonly it is known as the view factor, and today we will look into something which is known as the view factor analysis for any surfaces, be it a black surface or be it a real surface. You can always represent the radiation that is coming on from a surface in terms of its view factor, and that we will see today. And then we will look into something which is known as black body radiation exchange, because I mean until the last class we only saw the radiation that is emitted from a body owing to its own temperature, keeping in mind that we were not basically focusing on trying to understand what is the radiation that is being intercepted by other bodies. We are basically focusing our attention into understanding the radiation heat transfer in terms of its in terms of the natural environment of the body itself. But a question arises that we know that a body, given its own temperature, emits radiation, and there were all those things of radiosity and irradiation coming in. But the natural question arises is that, okay, if now I have a body at a given temperature, how much of its radiation is being intercepted by another body located at some distance from this body, which of course should be known. And then this is the question that we seek to answer. Okay, and that's why we we also need to develop an understanding of something which is known as radiation exchange between surfaces. Not only, trying to, limit our understanding into radiation from bodies itself, and then trying to broaden our perspective into, going into radiation exchanges between surfaces. So this is something that we will see today. That's why we will start off with something which is known as black body radiation exchange. And then we will see that in case of a black body, the radiosity itself becomes its emissive power. So for a black body radiation, we will in fact prove that there is only one kind of resistance, radiation resistances that come into the picture, and that's known as the space resistance, written in terms of its view vector. And we will see all those things. And I mean, you must have seen that already in the lecture classes, but we will have a quick recap of these things and the associated numericals that are associated, that can be formed based on these concepts. Okay. And finally, we will look into a glimpse of this thing, which is known as the radiation network. That is just like, conduction and convection. You can also effectively represent the radiation heat transfer using a radiation network analysis. Just what we did in this course for conduction networks. We will look into something which is known as radiation network, and then we will see radiation network for a black body, and then we will see the radiation network for any real body. Okay, so these are the things that we plan to discuss in this discussion. Let's see how far we can go. If we are left to discuss, if time runs out, we'll keep the remaining discussions into the next class, because we don't have much of the contents left now. So yeah, so let's see how far we can go, and then we will see. Okay, so let's begin. If no questions, let's begin by understanding something which is known as the view factors or the shape factors. Okay, and for that, I have, uh, taken a figure, and this is, of course, this figure is from the book of Intro Opera. So I've taken a figure which says that there is a surface now having a differential area of dA1. you know you can assume that it's a diffuse surface. It is exchanging radiation with another surface having a differential area of dAj. This surface is denoted as I, so I'll write it down. This is the ith surface and this is the jth surface. So this ith surface is a diffuse surface, okay, and you can also assume that this jth surface to be an equally diffuse surface. The total area of this surface, whose differential area is dAi, okay, is A1, okay. Its own temperature is Ti, that is also given, and the distance between the centers of these two surfaces, the separation distance between the centers of these two surfaces is given by R, okay, and the corresponding, angles with the normals of these surfaces with the, distance of separation, that is basically this, you can say this position vector, okay, are theta I and theta j. In short, the normals of the corresponding surfaces make an angle theta I and theta j respectively for the ith and the jth surface with the distance of separation that connects the centers of these two surfaces, okay. And also the total area of this entire surface, whose differential area is dAj, is Aj, and its own temperature is Tj, okay. Of course, from this figure, you can understand that both these surfaces will subtend corresponding solid angles onto one another. For instance, the solid angle, okay, that will be subtended by this surface onto the center of this surface is basically equal to d omega j, which I have written, which had been written in the figure as d omega ji. This is the solid angle that is being subtended by the surface j onto the surface I, and this dAi from the definition of solid angle can be very, elegantly written as dAj times cos theta j divided by this distance of separation, which is r square. Okay. I hope this is clear. The physical setup of this analysis is clear. So the natural question, what we will try to ask here, and here comes the the formation of these view factors, and here comes the definition of this view factor itself, is that if I ask you what is the fraction of energy, okay, that is leaving this surface AI that is intercepted by the surface J. If this is the question that I want to ask you, then you need to understand something which is known as the view factor Fij. Okay, because it's the very definition of this view factor Fij, okay, which asks us, so you can define this Fij as the fraction of radiation leaving surface I, okay, that is intercepted by surface J, okay. And try to realize that when I say fraction of radiation, I mean it could be emissive power, that is what percentage of the emissive power that is coming from body I is intercepted by body J, or it could be radiosity in case of real bodies, that what is the fraction of the radiosity that is leaving the surface I is intercepted by surface J. And all these things you can define formally by using something which is known as the view factor, and this Fij is known as the view factor of the surface I. And without going into the the detailed derivation of this view factor, although the idea is that just how, so these view factors can be determined from the starting how we define the intensity of radiation. Okay, so just that formal definition of from the formal definition of intensity of radiation, you can determine the the integral form of this view factor Fij. But you have already seen that in the lecture classes, so I'll not do it as a repetition. Instead, I will just formally write down that this Fij, that is the view factor of I, which signifies the fraction of radiation leaving surface I that is intercepted by surface J, is given as 1 upon AI, which is the total area of surface I, integral over the entire surface AI, integral over the entire surface AJ, cos theta I, cos theta J, okay, divided by pi times the r square, which is the separation distance, and this is AJ AI. Okay, this is the most the most fundamental definition of the view factor Fij. Okay, and you can sense that from this form itself, the definition of Fij you can derive it by using you can derive it from the definition of intensity of radiation that is being coming from a body I. Use the fact that you have assumed it to be a diffuse body, then you can replace the intensity of radiation as pi times as the emissive power by pi, and then you can doing some tricks in the algebra, you can basically come up with this form of with this integral form of the view factor Fij. Okay, so we'll not go into the detailed derivation of how this thing came, but as I have given you the hint, it comes from the definition of the intensity of radiation itself, which we saw some classes back. Okay, and of course this you have already seen it in your lecture classes of this week. Okay, so in other words, you can see that this Fij, which is basically the fraction of radiation leaving surface I, okay, that is intercepted by surface J, is equal to 1 upon the area of surface I times this integral, which and you can see this integral is this integral basically is an area integral, of course, that integrates over the entire area of surface I and entire area of surface J. But remember, this although I said that this form of this shape factor or the view factor is the most the fundamental definition of view factor, but there is an inherent assumption that always follow, and that I have already stated verbally some time back. So this form is true. So this form is true so long as the surfaces must be diffuse emitters and have uniform radiosity. So what it means is that, and of course you will see when you basically kind of see the definition, I mean the derivation of this view factor Fij, you will see that you have to use the fact that your surface is a diffuse emitter, typically because, as I said, that the derivation is, so the derivation of these view factors comes from the definition of intensity of radiation. And we saw that for diffuse bodies, your intensity of radiation is your emissive power divided by pi. So basically, if you want to, derive this form of view factor, you need to use this fact that your body is a diffuse emitter. And then also you need to, in the derivation itself, you also need to, you also need to assume that your body have a uniform radiosity, which means that the radiosity is not a function of the spatial locations within the body. That at any point, if you go, let's say I have a surface, at any point on the surface, if you go, it must have an equal radius. Okay, and these are the things that you should keep in mind when you are using this integral form of this view factor. Okay, so this is something that you guys need to understand. But apart from that, in all other circumstances, you can use this general integral definition of view factor to actually determine what is the view factor, which basically states what is the radiation energy that is leaving a surface I that is intercepted by surface J. All right. Similarly, I can also determine something which is known as similarly, I can also determine something which is known as Fji, and this is just the other way around. Just like Fij, which is the fraction of radiation leaving surface I, Fji will state that what is the fraction of radiation leaving surface J that will be intercepted by surface I. Okay, and if you just have a look at these form of the view factor, you can formally define Fji as 1 upon Aj. Now, if you write Fij, it will be the area of the ith surface. If you write Fji, that is, if you want to see what is the radiation energy that is leaving surface J that is intercepted by surface I, it will be 1 upon Aj, and then the integral will of course be the same. It will be integration from, so it will be integration of the ith surface, and by integration I mean an area integration of the ith surface and area integral of the jth surface times, these things will be same, cos theta I cos theta j by pi r square times aj, daj and dai, where daj and dai, as I have seen, are the differential areas of the entire surface area ai and aj respectively. Okay, for instance, if I have this, so for instance, if this is my entire, if this black surface is my entire surface, then this red, the red shaded portion is my differential dai, and correspondingly you can also determine the differential daj, which is of course the differential area of the entire area d of the entire area aj. Okay, so I hope the definitions of the view factors, at least the integral forms of the view factors, are clear to you. And just how you determine Fij, you can also equally determine Fji. You just need to reverse your understanding here. So Fji, as I repeat, is it's the radiation that is leaving surface J that is intercepted by surface I. Okay, and this is how you can basically formally define your Fji, that is the view factor corresponding to the surface J. Okay, so I'll just name this as some equation 1. I'll just name this as some equation 2. Okay, so if you now have a close look at this equation, so this integrand cos theta I cos theta j by pi r square of equation 1 and the integrand of equation 2 is exactly the same, which means I can straightforward write from 1 and 2. From 1 and 2, since the integrand within the integral is same, I can straight away write that my product of Fij times Ai has to be equal to the product of Fji times Aj. Okay, so this from 1 and 2, since the integrand is the same, I can always write Fij times Ai is equal to Fji times Aj. Okay, and this seemingly very simple yet very powerful relation in terms of view factor is known as the reciprocity relation, and I think that you have already saw this. in your lecture classes as well. So this product of Fij times Ai also it seems very simple, yet it is very powerful in view factor analysis, and that we will subsequently see when we solve a numerical associated with it. But anyways, this product of Fij times Ai is always equal to the product of Fji times Aj, and this relation is known as the view factor reciprocity relation. Okay, and this you have already, this you have already seen, I believe, if you go through the lecture series. But once again, you it's kind of a good recap, because this is a very powerful relation that you guys will appreciate it. Okay, so I name this as some equation 3. So it's all because this integrand cos theta I times cos theta j by pi r square is always the same. Be it we determine Fij, or be it we determine Fji, and that's why the product of this Fij times Ai is always equal to the product of this Fji times Aj, and from there we kind of can write the reciprocity relation as this Fij times Ai is equal to Fji times Aj. Okay, so this is known as the view factor reciprocity relation in radiation heat transfer. Okay. Also, one more thing that you need to understand, and then we will formally solve some numericals associated with this view factor, is that apart from this so we learned something which is known as the view factor reciprocity relation, that comes from the formal integral definition of the view factor itself. But apart from this, you also need to understand that if I have a surface I, if I have a surface I, okay, and then I want to see that, or if I now want to determine, or in other way around, if I have many other surfaces, let's say some arbitrary surfaces like this, okay, let's say this is surface 1, this is surface 2, this is surface 3, and in this way I can determine up to my ith surfaces. Okay, so basically what I want to portray here is that if I now have a surface I, which is basically a surface, let's say I will kind of formally make it a surface, let's say. So if this is a surface and I want to see, okay, and or in other words, I want to define view factors of these surfaces I with all the remaining surfaces which are there to intercept the radiation that is leaving surface I. Okay, so basically this surface I, if it's a diffuse surface, will emit radiation in all possible directions. Okay, and I want to understand that what are these terms f, I, Fi1, Fi2, up to this, let's say if I want to determine this n. So let's not name it as I, let's name it as some n surface, if there are total n surfaces there. Okay, so it's up to Fin. So always try to understand that these, so what is this Fi1? Fi1 is the radiation that is leaving surface I, is intercepted by surface 1. And similarly, I can always write that there could be one more, fraction of radiation that is leaving surface I, that can be intercepted by the second surface. And in this form, if you draw this analogy to the nth surfaces, which you can kind of think as like there are n surfaces which is basically surrounding this surface I, then you can always write that the summation of these view factors, for instance this Fi1 plus Fi2 plus dot 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 up to this Fin, this is always 1. Okay, and that you can appreciate, because the total energy that is leaving surface I is should be equally distributed to the nth to all the nth surfaces. Okay, and this is the second the most formal property of view vector, which is known as the summation rule. Okay, that is, if I add all the view vectors, okay, of surface I that could be intercepted by different nth surfaces that could be placed everywhere. You can also think of it like there is a surface I, and there are n enclosures that encloses these surfaces. Then the view factors of this surface I, that is the total view factors, should always add up to be equal to 1. Okay, and this is known as the summation rule. This is known as the summation rule of view factors. Okay, and I will kind of like name this as my fourth equation, or whatever you want to say, equation or a property or whatever you want to say. Okay, so these are the things that you need to understand. First, the integral, the integral forms of these view factors. How do you basically define Fij, and equivalently, how do you basically define Fji? And then from the integral form, since the integrand is the same, you can always write that the product of Fij times Ai equal to Fji times Aj. And you can of course extend this to n number of n and m number of surfaces having you know so if there are n, so for instance you can also extend this to a third surface, and so long and so forth. Okay, so long as the integrand within this integration remains the same. Okay, so for any generic surfaces I and j, you can use this what we call as the reciprocity view factor relation. And also for any generic surface I, the summation of all the view factors associated with this surface I, which I have stated that all these radiant energy can be treated as like they will be intercepted by n surfaces spaced in the spaced arbitrarily in the space. You can always write that the associated view factors of this surface I, that is all the view factors associated with this surface I, if you add them up, they will obviously turn out to be equal to 1. Okay, and this is known as the summation rule of view factors. So these four relations or four equations are very much powerful if you want to uh, kind of understand the analysis of view factors. And we will see shortly by some numericals how we will use these relations into basically solving numericals of these forms. Okay, but yeah, so I agree, although I did not derive how this equation would look like, but this derivation is done in the lecture classes. Please please go back if you are not so clear about it. Please go back and have a look at this derivation. It's important if you want to understand what basically the view factor Fij means. But I hinted that this comes from the very definition of the intensity of radiation that is leaving a surface I. Okay, and using the fact that your intensity of radiation is equal to your emissive power divided by pi for a diffuse body, you can formally define your view factor Fij. Okay, so this is something that you guys need to understand. Still, I would say if there are any doubts onto how this thing came, please go back and have a look at your lecture series. Okay, but in a nutshell, these are this equation 1, this equation 2, this 3 and 4 are what in principle you all need to know if you want to solve any problems associated with view factors. And shortly we will see how we can apply these relations. Okay, so I stop here for some time. If you have any doubts, you can ask me, or else we'll proceed with solving some numericals associated with this view factor analysis. Okay, so if no questions, let's try to solve the first problem, okay, associated with this view factor. So it says that for an enclosure with n surfaces, how many view factors need to be determined directly? Okay, it's a very straightforward question that they're asking, that if I have an enclosure, for instance, I will just draw an enclosure, maybe like this, like this, like this, this, and this could be there could be n number of surfaces with between these. So I'll just basically draw some dotted lines. Okay, so this dotted line means that there could be n number of surfaces in between these. So what they're saying is that if I now have an enclosure, okay, if I now have an enclosure with n surfaces, for instance, if I name this surface as 1, this surface as 2, this surface as 3, and so long and so forth, you can determine all these surfaces up to the nth surface, which is this n. Okay, so if I now have these n surfaces, and you can always assign a view factor corresponding to these n surfaces. For instance, for surface 1, I can have f11, I can have f12, and I can have f1n. Similarly, for surface 2, I can have f21 up to f2n, and so long and so forth for the nth surfaces fnn. Okay, so the question is, you can always assign a view factor corresponding to a particular surface. I mean, you can always assign this view factor Fij corresponding to, all the ith surfaces that we have considered. So given that, what they are asking is that if now I have an enclosure of these n surfaces, how many view factors should you directly know, basically to know all the view factors. Okay, so the question is, it's a straightforward question, that if there are n surfaces, so if now I have n surfaces, okay, just hold on. Okay, so the question is, if I have an n surfaces, the maximum number of view factors that can, that can be possible corresponding to this n surfaces is basically equal to n square. And that, of course, you can easily, easily, acknowledge, because if let's say I have two surfaces, 1 and 2, there will be 4 view factors. That will be f11, f12, f21, and f22. Okay. Similarly, if I have 3 surfaces, there would be, 9 view factors, which is 3 squared. So in general, if I have n surfaces, this is something that you need to understand. If I have n surfaces, there will be as many as n square view factors. So this is the maximum number of view factors that can be possible for n number of surfaces. So if I have n surfaces, n square is the total number of view factors. Number of, I would say, possible view factors. Okay. Now, it is important that you don't need to directly know this n square number of view factors a priori, which means because we have some important relations associated with view factors, okay, some of these view factors need not to be known directly, or in other words, you can basically determine what these view factors would be, and the other view factors you need to know directly. So the question is asking that how many view factors should be known directly, provided you have this n square number of total view factors coming from n number of surfaces. Okay, I hope the question is clear. Okay, so they are just asking us that how many view factors should be determined directly. That's the thing that they are asking, and we have determined that if I now have an n surfaces, there will be an n square of the total number of view factors that are possible. Okay, so what I would now do is, for the ease of understanding, I will now basically describe something which is known as the view factor matrix, or in other words, this n square number of view factors, you can write it in a matrix form, and this will be, so we write this for the ease of understanding, of basically to find out how many view factors need to be determined directly. Okay, so this view factor matrix, this view factor matrix, sorry, can be written like this. So for a first surface, I can have f11. Okay, that is so what is f11? It is the fraction of radiation that is leaving surface 1 that can be intercepted back by surface 1 itself. Okay, and of course this is possible. For instance, if I have, let's say, a circular cavity, then the radiation that is leaving this cavity will be intercepted somewhere here. So it can be possible that for curved objects or circular objects, there could be some fraction of radiation that if it leaves the particular surface, could be intercepted by the surface itself, and that is known as f11, or in general you can write it as FII. Okay, that is the fraction of radiation leaving surface I is intercepted back by surface I itself. Similarly, I can have f12, that is fraction of radiation leaving surface 1 intercepted by surface 2, and this could in general be extended up to f1n. Okay, so this is the first row corresponding to the first surface, and these are the view factors corresponding to the first surfaces. Okay, so what I meant to say is that these row, okay, these row are the view factors of surface 1, and similarly for the second surface I can write what, f21, f22, and this can be extended to f2n. And similarly for the third surface as well, you can write f31, f32, f33, extended up to f3n. And if you draw the same analogy for the nth surface, you can just write fn1, fn2, and this will extend up to fnn for the nth surface. So since I said these are the view factors associated with surface 1, drawing the same analogy, this will be my view factors associated with surface 2, and my view factors associated with surface 3, and so long and so forth. The view factors are associated with my nth surface. And as you can appreciate, I have n number of rows in this view factor matrix and n number of columns in this view factor matrix, which means the total number of possible view factors that can arise from an nth zone enclosure is n squared. Okay, again, that is not what the question is asking us. The question is asking us that if there are n surfaces, meaning that there are n square view factors, how many view factors do we need to know directly, and how many view factors comes from the relations, for instance the reciprocity relations and the summation rule. Okay, so this matrix that I wrote here is known as so this, whatever you call it, so I call it generally as my view factor matrix for n surfaces. And just by looking at this matrix, you can verify that there will be n square number of view factors, because the product of the rows and columns is equal to n squared. Okay, now it is important to understand that. Let's now figure out how many view factors can be obtained directly using the summation rule and the reciprocity relation. For instance, for the surface 1, I can write that the summation of f11 plus f12 plus f13 up to this f1n, this is basically equal to 1. So from the surface 1 itself, I have one relation, one summation relation. Okay. Similarly, from surface 2, I will have a second summation relation, and from surface 3, I will have the third summation relation. And if I draw this analogy up to the fourth surface, I will have, n summation relation. Which means that out of these n square view factors, n number of view factors can be determined by using n number of summation rule, because the summation rule will give us n number of equations, as we just now saw. If we just write the summation rule for all these rows, okay, I can simply say that there will be n number of summation rules that will come from this n number of surfaces, which means n number of view factors out of this n square view factor can be determined from the surface, from the summation rule. Okay, so I'll write down here that n view factors can be determined from n summation summation rules. Okay, so this is simple, right? Because it's very simple, because from one summation rule, that is, if I just write down this summation rule for the surface 1, I can determine at least one view vector, because this is giving me one equation. Okay, for instance, if I say that I give you n minus 1 view vector for this surface 1, I can easily determine the nth view vector, because I have one equation here and I have just one unknown corresponding to one equation, which means that if I have n summation rules, I can always determine I can at least determine n view vectors corresponding to these n summation relations that I have. Okay, so that is what we wrote here. Now, not only the summation rule, I also have something which is known as the reciprocity relation. Okay, that is basically the fact that my Fij times Ai is equal to Fji times Aj, the thing that we just now saw. So you need to understand that from from all these reciprocity relations, that if I kind of write down the reciprocity relation for all these n surfaces, there will be n into n minus 1 by 2 reciprocity relations. Okay, so what I am trying to say is that there will be, or I would say there would be n into n minus 1 by 2 reciprocity relation. Okay, Just by using a simple permutation combination, you can basically find out that this number will always be equal to n into n minus 1 by 2. For instance, you can verify if you have two surfaces, okay, which means n is basically equal to 2. If you substitute here, you will basically get 2 into 1 divided by 2, okay, which means for two surfaces, you will have a single reciprocity relation, okay. For instance, if you have three surfaces, you will basically have, you know, so if you put n to be equal to 2, so for example, if your n is basically equal to 2, so you will have 2 into 1 by 2, which is equal to 1 reciprocity relation. And that is obvious, right? Because if I have two surfaces, the total number of view factors would be f11, f12, f21, and f22. Okay, and the total number of reciprocity relations will be so the total number of reciprocity relation is just one, because I will just have a1 times f12 is equal to a2 times f21. Okay, so if I have two surfaces, I will have four view factors and just one reciprocity relation. And also I have something which is known as the summation rule, which means that this f11 plus f12 plus f21 plus f22 basically equal to 1. Okay, which means if I have two surfaces, I will have four view factors, okay, and I will have one reciprocity relation and one summation rule. Okay, which means out of these four view factors, one view factor will be obtained from this reciprocity relation and one view factor will be obtained from this summation rule. Okay, now this summation rule, sorry, I made a mistake here. There will be, so this is summation rule for surface 1, and I can also write a summation rule for these surfaces, which is f21 plus f22, okay, plus, did I make a mistake here? So f11, okay, sorry, I wrote it. Sorry for the confusion. This is f11 plus f12 equal to 1. This is for surface 1, and I have f21 plus f22, and this is equal to 1, and this is for surface 2. So this is for surface 1, and this is for surface 2. Okay, so if I want to summarize, for two surfaces, I will have, so for two surfaces, I will have basically four view factors, that is 2 square, which is equal to 4. I will have one reciprocity relation, and I will have, two summation rule from, two summation equation, which means out of these four, if I have total of four view factors, one can be obtained from the reciprocity relation. Okay, two can be obtained from the summation rule. Which means that I just need to determine one view factor directly. Okay, one needs to be determined directly. I hope you can understand what I'm trying to say here. Okay, if you kind of now draw the same analogy for n number of surfaces, okay, which we basically did here. For n surfaces, there will be n square view factors. N number of view factors out of these n square view factors can be determined from the summation rule, and n into n minus 1 by 2 number of view factors can be determined from the reciprocity relation. So therefore, for n surfaces, if I subtract the known view factors coming from the reciprocity relation and the summation rule, that will basically be n square minus n, the view factors coming, okay, I'll write it in different color, maybe n. So this n comes from the summation rule minus, n into n minus 1 by 2. Okay, so these many view factors needs to be determined directly. Okay, needs to be determined directly. Because, as I repeat, for n surfaces, there will be a total of n square view vectors, out of which n number of view vectors will come from the summation rule, and n into n minus 1 number of view vector will come from the reciprocity relation. Okay, which means if you subtract the known view vectors, because you have these many equations, the other remaining view vectors need to be, you need to know basically what exactly is this view vector. To know all the view vectors corresponding to n, enclosures, if you determine each, each view, if you determine view vectors corresponding to each n surfaces of the enclosure. Okay, so this is what the question is asking us, that how many view vectors need to be determined directly. So basically you need to determine these many view vectors directly. Okay, it is n square minus n minus of n into n minus 1 by 2, and if you just calculate this, okay, so what will you get if you just calculate this n square minus n minus, this is basically equal to n square minus n by 2. This is just, what, n square minus n square by 2, and this is what, minus n minus of, I think this will be plus, okay, minus n minus plus n by 2. I think we'll just end up getting what, I think we'll just end up getting, this is n square, this should be just n square by 2 minus of n, which means it is just n into n minus 1 by 2. Okay, so that's the answer. So n into n minus 1 by 2 view vectors so you need to directly determine, or you need to directly know this n into n minus 1 by view vectors out of, out of n square total view vectors. All right. I hope this is clear. I hope the question and the solution is clear. It's just that we need to see how many view vectors you need to basically, so you just need to see how many view vectors can be obtained from the, the summation rule and the reciprocity relations. Okay. And from there, you can basically calculate how many view vectors, you need to know directly for calculating all the view vectors corresponding to the n surfaces in an enclosure. Okay. I hope this is clear. I'll wait here for a couple of minutes. If you have any questions, you can ask here. So a simplified form you can always verify when you take n equal to 2 and see how many reciprocity relation you will get and how many summation rule you will basically get from here. Okay. For instance, this, if you have n equal to 3, let's say if you have n equal to 3, this means you need 3 into 2 by 2, which means you need, so at least 3 vectors vectors you need to know directly. That's what this formula says. Okay. All right. So I hope you're clear with this problem. Let's move on to the next problem. Which says that, so I hope you can see the problem on your screen. So it says that consider a diffuse circular disk of diameter d and area aj, which means there is a disk. Its diameter is d and its area is aj, which is responsible for emitting radiation. And a plane diffuse surface of ai very much less than aj, which means this ai is a differential surface. And it means that the area of this ai is very small with respect to the area of aj, and the surfaces are parallel. And ai, that this ith surface is located at a distance of l from the center of aj. Okay, so what they are saying is that the distance between this very small surface ai and this surface aj, the distance between their centers is l, and this is how the orientation of ai and aj is there in space. Okay, it is given that, you need to understand, it is given that this ai is very less than aj, which means the area, the magnitude of area, that, so it just says that this area is very much less in magnitude than the corresponding area of aj. Now given this scenario, what they are asking is that you need to obtain an expression for the view factor fij. So what you need to find is, so you need to find fij. This is all that you need to do. Given this orientation of ai and aj, given the areas of these two objects which we know, It is also given that for the larger area, that is for AJ, the diameter is D and its area is AJ. Okay, and the distance between the centers of these two areas is given by L. Now, given this scenario, what you need to do is you need to basically find out what is the view factor that is, or you need to find out Fij, which means the radiation that is leaving surface I that is intercepted by surface J. Okay, or what is the fraction of radiation that is leaving surface I and is intercepted by surface J. That's all that you need to do. Okay, I'll give you some time to think how to approach this problem, and then I'll proceed with the solution of this form. Okay, I forgot to state one thing. You can assume that these things. You can assume that all surfaces are diffuse, and of course I already mentioned that AI is very much less than AJ, and you can assume that there is there is uniform radiosity on surface AI. Okay, you can just assume these things, okay, to basically calculate your Fij here. Okay, I'll give you a couple of time to basically think about this question. How can you basically approach this? And anyway, I will state the answer. There's some, after 1 or 2 minutes. Or at least I will show you the procedure for calculating the view factor Fij. Okay, so the approach is simple and we have already seen. So what we need to do is, at least you guys, uh, just by looking at the figure, you guys have at least thought that, or at least there should be, certain, you know, there should be a certain way you need to basically solve this problem in order to get Fij. And one of these ways is to use these integral forms of view factors, because we have seen so when we stated the integral form of the view factor, we have seen that we just consider similar surfaces of these forms only. Okay, so what I am saying that what we will do is, from the definition of Fij that we just now saw by equation 1, which is basically this form. Okay, we can directly write. So what can we write? So from the definition of Fij, I can write that my Fij using equation 1, as we just now saw, can be written as 1 upon AI. Okay, integral over AI, integral over AJ times cos of theta I cos of theta j divided by pi times the square of the separation distance multiplied by what? Multiplied by dAi, dAj, which are just the differential areas. Okay, so this is obtained from equation 1, that is the integral form of the view factor. Okay, so what we will do is, we will do some simplification. So you can appreciate that the normal of the surface I, that is n cap, is equal to the normal of the surface J, which is also equal to n cap, because the normal of this surface is pointing towards this direction, the normal of this surface is pointing towards this direction, which means that my cos theta I should now be equal to cos theta j. That has to be. Okay, it was simply different cos theta I and cos theta j. It would have been different if the normals, let's say I have surface I, let's say I have the larger surfaces like this and the other surfaces like this. if I have this orientation, then the normal would basically point towards this, and this normal would point towards some other arbitrary direction. But since the surfaces are now parallel, it has to be that since their normals are pointing towards each other, this cos theta I, that is this, that basically is, so if I take a differential, let's say surface here, this would be my cos theta j, and if I take a differential surface here, this would be my cos theta I, and this, and since these normals are, basically facing each other, meaning that if I just now, draw this, things would be clearer. This would have been my cos theta I, which is this, and this would have been my cos theta j. And just by using simple mathematics, you can prove that your cos theta I is equal to cos theta j. This is so because the disks, or this area, that is this disk area, which is AJ, and this small area AI, they are basically lying parallel to one another. And this is already given to your, already given in the problem, that the surfaces are parallel. So you can write that your cos theta I is basically equal to cos theta j, and you can just write as some generic theta, let's say. You can just write cos theta I is equal to cos theta j, and this is just some, let's say some cos theta. Okay. All right. So what I can now do is, since their normals, and of course I'm writing this because my surfaces are parallel. So I can now write this Fij as 1 upon AI, okay, integral over AI, integral over Aj. This becomes cos square theta by pi r squared times dAi dAj. And now, since this cos, see, this cos theta is what? This cos theta is basically, so it's either of this angle or it's either this angle. Or you can simply write that your cos theta is nothing but, it's just nothing but L by R, just from this geometry. Okay? Because it's obvious, right? Because this is your R, that is the radius of this disk. Sorry. I think I made the mistake. Yeah, this is your R. I think I made a mistake here. Okay, sorry, this is not R. So this is of course d by 2. That's different. This is your d by 2. The R is basically this distance. It's basically the distance that, so if you take a differential area here, it's basically this, the center to center distance of this differential area to this, of course, this area AI. Okay? Or in other words, I'll make things clear. What basically is this cos theta. So it's that I have a disk here. It's that I have a disk here, and let's draw it in nice. Let's draw it in a better way. I have a disk here of this form, okay, and I have a small area which are parallel of this form, okay, and I said that the center to center distance, the center to center distance is given as L. Now what I can do is I can always take any generic R, and make a ring of radius R, and then take a differential area dr, which can be like this. This width of this differential area is dr, and in this differential area, if I pick a generic surface, let's say J, which is basically this. This is my, so this is my generic surface. I'll just write. So this is my generic surface J. So this is my surface I. This is my surface J. And then if I kind of, draw the center to center distance from these surfaces I and J, which is like this. Okay. And then this distance I call it as R. Then I can always write my cos theta. If this is theta, this has to be theta. Then I can write, my cos theta as equal to L upon R, because it's just the perpendicular to the hypotenuse. Okay, I hope this is clear. And this differential surface is, so what I can write is that this differential, so this is my differential surface. Okay, so I can easily write that my dAj, which is the elemental area of this differential surface, is nothing but 2 pi r dr. That's it. Okay, so that's what we will be using in this equation. I hope this picture is clear. What is R and what is L at least, and why I can write cos theta as L by R, and how to basically make, formulate this differential surface. Because remember, this form of view factors, these are true for differential surfaces only. So since my surface, my disk is a generic disk, I need to, take a strip into onto this and basically calculate what will be, the fraction of radiation in, leaving this surface I will be intercepted by this generic surface, and then I will integrate it over the entire, over the entire radius of the disk. That is simply because your cos theta is, this angle will obviously vary when I move from, my center to the extreme end of the disk. Okay, so what we'll do is we'll pick a generic theta, and in that theta we'll try to calculate what will be my, what will be my Fij basically, and then we'll integrate it from, maybe from 0 to t by 2 to be precise. Okay, so this is the idea how we will use this, Fij, and let's now try it out. So one more simplification I will do. What I will do is I can write this as integral over ai dai, because your dai is not a function of theta, because that is only because this I is a differential surface, and that's the assumption why it is taken, that your ai is very much less than, ai is very much less than your aj. So what I can do is I can take this dai out of this, I can take this out, and then I can simply write it as integral over aj times cos square theta by pi r square, okay, times daj, where this r is again this, this, it's the center to center distance of this differential strip and this differential strip. Okay, I mean, please don't confuse about this r and the other dimensions. Okay, and of course I know that this disk, the entire radius of this disk is of course d by 2. Okay, I hope things are clear. So this is your Fij. So what I can now do is what will, so this is easy to calculate, because this will just give me what? This will just give me ai. So Fij can now be written as 1 upon ai times ai into, I need to integrate this, this integral over the entire surface of aj. So that gives me integral over aj cos square theta by pi r square times daj. So daj, as we know, is just 2 pi r dr. Okay, that is basically the area of this strip which we have taken into consideration. So this becomes what? This becomes times 2 pi r dr. Okay, so this aj and aj would cancel each other. And if I just simplify, I write it one more time, it just becomes Fij as integral over aj. Okay, this is cos square theta by pi r square times 2 pi r dr. Okay, please don't confuse this small r and capital R. Always remember, this small r is nothing but a generic radius of this strip that I have made, having an area 2 pi r dr, and this capital R is the center to center distance of this differential area, of this differential shaded area to with the center to center distance of, with the central distance of this, area ai. Or in other words, r is basically, this r is basically the center to center distance of the differential area aj to the, to the center of the differential area ai, the capital R, of course. Okay, please don't confuse that. Now what I can do is I can just, make this pi's cancel out, and then we can do one more thing. So I can always write my r, so just by using the simple, what people call is at the Pythagoras theorem, this r can now be simply written as r square equal to L square plus small r square. Okay, that is typically because from this right angle triangle, from this, maybe I'll draw it with a different color, that is from this, this right angle triangle, that is basically this. And of course, since this is, so if I just draw this right angle triangle, if I just, draw this right angle triangle here, it is just like this. So this So this is L, this is my capital R, this is my capital R, and this happens to be my small r. Okay, so this is L, this is capital R, and this is small r, and this is the theta that we are considering. And remember, these are the two differential areas that we considered. I think things will be much more clear here. This is my area DAJ, and this is my area, DAI. And this DAJ, if you remember, this was kind of the strip. So if this was the strip that we considered, so it was kind of like this. Okay, I think now the picture is clear. Okay, so that's why I can write R as L square plus R square. Okay, and what I will do is I will just substitute this thing here. So what I can do. Oh, and also we'll do one more thing. So since I know my cos theta is basically equal. So what is cos theta? Cos theta is equal to L by R. That is from this. Okay, and of course from here also you can interpret that your cos theta has to be equal to L by R. This just becomes L by R, and we'll just substitute all those things into this expression, and then your Fij becomes what? It is just, so Fij is, so now I can just integrate it. So since now it's just the radial integration, because it's kind of an axisymmetric problem that we are trying to see. That's why I'll just integrate it from 0 to d by 2. Okay, then cos square theta is nothing but L squared by R square times 1 by R square. So 1 by R square would become what? So it will become, I think we're doing it correctly, right? Okay, so 1 by R square is what? So 1 by R square is just L square plus small r square. And then what I will do is, and of course you need to integrate it from R dr. Okay, and then what can we do? I think we missed a 2 here. Okay, I think we missed, okay, so there is a 2 here also. There is a 2 here also, so this becomes 2r. All right, and of course this r can also be written as L square plus small r square. So this Fij, can now be written as integral from 0 to d by 2. This just becomes L square plus R square and whole square, because this r is just nothing but L square plus R square itself. And then I have an L square, 2L square here, and this integration is in terms of R dr. So this 2L square basically comes out of the integral because this distance is fixed. That is typically because this distance is fixed. Okay, and that's why I can write it as Fij as 2L square times integral 0 to d by 2. Okay, it is R dr by R square plus L square. And if you do this integration, so if you just perform this integration, we'll not do it now for the sake of time. If you just do this integration, you'll get your result as Fij as b square by t square plus 4L square, to be precise. Okay, that's it. That is your, that is your Fij in this question that they are asking you to basically evaluate. So I hope the problem is clear. This is one of the most fundamental, problem on, view factor, where there is a differential area DAI, and it is emitting radiation. And what is the radiation, or, what is the radiosity that is leaving surface I is intercepted by a disk, which is parallel to surface I, but instead of it being a differential area, it now have a finite area. Just because it have a finite area, we need to do the analysis for a small strip. Typically, because your view factor will depend upon which area that you are, I mean, the definition of view factor is basically, so we started the definition of the view factor in the integral form by, writing it for two differential areas, and that's why we need to do the analysis for a differential area, and that's why we made that strip. And then we need for the entire, disk, you need to integrate it from 0 to the distance d by 2. Okay, so that's the idea, how to basically calculate this view factor. And then we have used the help of mathematics to basically formulate how to calculate the center to center distance and all those things. See, had this been a small differential area lying in L, the analysis would be just straightforward. But since it's a disk now, and because the center to center distance will keep on changing, you know, when I move along, along this direction in the disk, and that's why we took a generic, generic point, let's say generic, differential area DAJ, calculated the view factor for this differential area, and then the entire view factor would be just the integration when this area basically moves from this point to this point, and that's the idea behind calculating this view factor. Okay, I hope this is clear. That we saw from this simplified figure also that I just now you know draw here, just now drew here. Okay, I hope this is clear. This is how we basically calculated the view factor Fij for this problem. If you have any doubts, I'll stop here for some time. If you have any doubts, you can ask me. If not, we will see one or two couple of interesting problems on on view factors itself, and then we'll move into the other parts of the discussion here. In the meanwhile, if you are done, you can have a look at this next problem. So basically, you are given some geometries, geometry 1, geometry 2, and 3, and all you need to do is determine the view factors f1 and 2, where the areas 1, 2, and of course here we have the third areas are given, are given in the problem. So you can basically say that for this problem, there is a sphere of diameter d that is inside a cubical box whose length is equal to the diameter of the sphere. In that context, you need to determine this f12 and f21. And so long, the same analogy goes for this problem and this problem. Okay, if no other questions on the earlier problem, I hope the problem is clear. If you have any questions, please feel free to use the discussion forum of the course, and please drop your questions there, and I'll be happy to explain, like, if you have any doubts associated with the questions, not only of this discussion, but also like if you have doubts associated with the questions of of the assignments. Although I will not directly give the answer to the assignment questions, that is against the principle, but at least we can try off by giving some hints, or like help you in finding out the at least not the entire solution, but at least some parts of it, so that you can get at least a roadmap of solving the problems. All right, so if no doubts, then let's see this problem. So you were given three scenarios. One, a sphere lying inside a cube. Two, there is a diagonal partition in a long square duct, which is basically placed like this. And third, there is a circular tube of equal length and diameter. Okay, in all these three scenarios, what you need to do is you need to determine the view factor f12 and the view factor f21. Okay, so let's start from the first problem, and let's see how can we determine the view factor. So for problem 1, you are given that there is a sphere, okay, of diameter d and a cubical box of length L equal to d, which means that this length, or in fact the sphere, perfectly fits into the cubical box. Basically, that's something you can interpret. Okay, so now, so how do we determine this? So here my surface 1 is the sphere, my surface 2 is basically the box. F12 is just what is the what is the radiation that is being coming from this surface 1 is intercepted by this square box, or the cubical box. Okay, so one thing you can do here, that here I have, so how many surfaces do we have? So I have two surfaces. Okay, but from these two surfaces I will have total of 4 view factors. From these two surfaces, I'll have total of 4 view factors. That we know because we just now saw that If I have n surfaces, we'll have n square view vectors. But from these 4 view vectors, I will have, 2 summation rule, 2 summation rule from which I can determine 2 view vectors. This view vector, I'll just write it as VF. From here, I can determine 2 view vectors from the summation rule. And I also have one reciprocity relation from which I can determine one view vector. So there is one still remaining view vector, okay, that needs to be determined directly. But luckily or unluckily, we have an escape here. And think about it, that how can we basically determine that unknown one view vector that is still left to, in order to calculate all the remaining view vectors. So I'll give you a hint. It's from the nature of the problem that one view vector will just go out to be equal to 0. But before that, so what we need to calculate is basically we need to find f12 and f21. That is what we need to do. And as I have stated, that we have 2 summation rule from which we'll get 2 view vectors. We'll have one reciprocity relation from which we'll get 1 view vector. But still, since there are 4 view vectors, I still need one more view vector basically to close the system. But as I said, from the nature of the problem, from the from the nature of the problem that we are given, or the physical picture will assist us in this regard to calculate the unknown directly. So the unknown view vector that we should get directly will be achieved from the nature of the problem itself, that is from the physical space that we are given. Okay, so as you can see, I'll tell you the answer. As you can see this sphere, okay, the sphere is basically radiating from its surface in this manner, okay, which means if you ask me what will be this, so which means if you ask me that what will be this f12, it just means that whatever the radiation, okay, so it just means that whatever the radiation that is coming from the surface 2 is intercepted by surface 1, okay, and in this context all of the radiation that is coming from the surface 2 has to be intercepted by surface 1 itself, right? Because this sphere is completely enclosed by this cubical box. So, and since the sphere is radiating in the outward direction, whatever the radiation that goes out of the sphere has to be intercepted by all the walls of this cube, right? Which means just by inspection, I can write that f21 is basically equals to 1. Okay? And this is so because, all the radiation, or you can just write that this is so because the sphere is enclosed inside the cubical box. Okay, which means I directly know f12, and for f21, okay, I can just use the reciprocity relation, which means from so this f12, this we already got by inspection. That's what I'm trying to say here. Okay, drawing the logic that since this cube is inside this, since this sphere is inside this cube, whatever, and this sphere is basically emitting radiation in all possible directions. Okay, this sphere is kind of emitting radiation in all possible directions, and although I have shown it exaggeratedly, this radiation basically cannot go out of this cube. Okay, which means that whatever the radiation that this sphere emits has to fall on the surface of this cube, and drawing the same analogy and drawing the same exact analogy, I said that this f12 is equal to 1. I mean, it's not analogy. It means that drawing the same conclusion, I can say that f12 is basically equal to 1. And now from from the view factor reciprocity relation, I can say that, what can I say? I can say that a1 f12 is equal to a2 f21, which means I require f21 now, which means I can write that f21 is equal to a1 by a2 times f12. Now I know A1 and A2 because these are some just spherical. I mean, A1 is just a spherical geometry, which means it would be just pi d square by 6 L square times F12 is basically equal to 1. Okay, I hope this is clear. This is nothing but just the surface area of the sphere. This is nothing but the surface area of the cube. So this means my F21, and since I know that my L is basically equal to D, therefore this F21 is nothing but equal to pi by 6. That's it. These are the two view factors that the question is asking us to find. Okay, this is F12 and this is F21. Now you need to also understand that since, from here, you can also, interpret that if you just use the summation rule, since F12 is equal to 1, and you also know that, F11 plus F12 is equal to 1, that is from the summation rule. You can also interpret, although the question has not asked you, you can also interpret that your F11 has to be equals to 0. This is because your F12 is basically equal to 1, and that we have, said by inspection. So this is obtained, from the very fact that your F12 is basically equal to 1, which means, what does it mean? It means that the meaning that F11 is equal to 0 is the fact that there is no radiation that will, leave the sphere and will fall on the sphere itself. And that's obvious, right? Because it is just radiating heat outside, which means it cannot, so there is no possible way out of which, the radiating heat that is coming, that is, leaving the surface will fall on the surface. And that's why this F11 has to be equals to 0. Okay, so this is the another view factor that we can basically see. And also, just by using the summation rule for the second surface, you can argue that your F21 plus F22 is equal to 0, sorry, is equal to 1, and your F22 is nothing but 1 minus of F21, and then your, F22 basically becomes equal to 1 minus of pi by 6, which is equal to 5 pi by 6. And this is the other view factor F22. Although this is not what the question has asked, the question has asked just to calculate F12 and F21, but in general, this will be all the view factors that are possible from this given scenario. Okay, I hope the things are clear. And since also this is also a test, it's a testimony to the fact that if I have two surfaces, I will always have, two square view factors, and that's why I had F12, F11, F21, and F22. So I have 4 view factors, out of which 3 view factors came from the summation and the reciprocity rule, which are basically this. This view factor came from the summation rule, this also came from the reciprocity relation, and this from the summation rule. And one view factor needs to be determined directly, as we just now saw. And that view factor, we argued that it will be equal to 1 just by inspection. Okay, so this is also a testimony to the problem that we already saw, and also it's a good it's a good solid proof that if you have n if you have n surfaces now, let's say, you will basically need to know n into n minus 1 by 2 view factors directly, and the rest view factor you can determine. So if you have n surfaces, you will have n summation rule, out of which you can draw n view factors, and you will have n into n minus 1 by 2 reciprocity relation, out of which you can draw that many view factors. And if you subtract these two effects, you will get how many view factors you need to know directly. And if the nature of the problem is there to assist you, you can basically calculate the view factors from inspection itself, just how we saw in this case. Okay, but this is not always true. But here, just because the physical problem is such that we can calculate one view factor just by inspection, we have basically done that. Okay, so we'll do one more problem here. The third problem I'll leave you as a homework. You can try it out at your home. We will also try problem 2. Okay, the hint for doing third problem is that try to calculate what will be the view factor between two coaxial disks. Okay, take help of the book of Introvera and try to calculate what will be the view factor between two coaxial disks, and then you can calculate all the other remaining view factors that you need to find out. Okay, but we'll try to do problem 2. We'll try to do problem 2. Now problem 3 you can try it at your home. If you find difficulty, I'll discuss this in the next class. Okay, so in problem 2 it says that there is a long square duct of this form. Okay, and there's a partition which is dividing the square duct into two surfaces, as you can, or into two volumes, as you can see here. Okay, so in this case, you need to basically calculate what is F12 and F21, where this 1 is your partition, 2 is this surface, and 3 is of course this surface. That is what they are asking us to do. Okay, so we'll draw the same, we'll just draw the same analogy, but I'll just draw the physical picture here just for you to make things clear. So the surface is kind of like this. This is the partition, and this is 1. Okay, and I think this is 2, this is 2, and this is 3. Okay, this is 2 and this is 3. So now straight away I can write that from from the summation rule, from the summation rule. Sorry. So from the summation rule, I can just write that F11 plus F12 plus F13 is equal to 1. But again, by inspection, I can directly say that since this is just a partition, it's just a straight partition, there is in no way the fraction of energy leaving surface 1 can fall back onto surface 2. That is typically because it will basically radiate in this direction, in all possible direction, of course, but it can no way come and fall back here. Okay, so this means I can straight away say that my F11, I can straight away say that my F11 is equal to 0, that again by inspection, and then I can just write that F12 plus F13 is equals to 1. And now one more thing that you need to understand is that since this is a square, okay, there is one more hint, that due to the symmetric nature of the problem, the total radiation that will come from this surface 1 will be equally divided onto the surface 2 and surface 3, meaning that my F12 should be equal to F13, and since their both summation is equal to 1, the symmetric nature of the problem will assist us here, and will say that my F12 and F13 should be equal to 0.5. That is solely because of the symmetry of the problem. Okay, so this is by symmetry. So this means that since my F12 and F13 are both equal to 1, and also I can just now say that F12 is just equal to 0.5. Okay, this is the unknown F12 that we need to calculate. And also, since we need to calculate F21, I will again use what is basically known as the reciprocity relation. So from the reciprocity relation, what I can say? I can say that my A1 F12 is equal to A2 F21, which means my F21 will be equal to now A1 by A2 times F12. Okay, now if I just consider that my width is just 1, then if I just calculate it at per unit width, my A1 is just nothing but, so the diagonal is just nothing but root 2 times the length, and my A2 is just L, which now means that this is just root 2 times L by L into 0.5. This now, so L and L will of course cancel. That means I have F21 as root 2 times 0.5, and root 2 times 0.5 is roughly around 0.71. Okay, which means my F21, that is the another view factor, is just 0.71. That's it, guys. Okay, so these are the unknown view factors F12 and F21 for this problem. Okay, so that being said, you need to be little bit clever when you are calculating this view factor. That is, from inspection also you can determine various view factors, and then for you always have the summation rule and the reciprocity relation to calculate the other unknown view factors. Okay, so that's the idea uh, into calculating view factors of these sort of geometries, uh, and I hope this is clear to you how did we basically go on and tackle this problem. Okay, I'll again stop here for some times. If you have, so problem three, so this is at homework. We have solved problem one and two. Problem three, you need to do it at your home. I'll discuss it in the next class, of course. Uh, of course, I gave you the hint that try to understand what will be the view factor between two coaxial disks, and that will help you to basically, solve this problem. If you have any doubt associated with problem one and two that we just now solved, feel free to, speak out here. Okay, if no doubts, so we'll learn one last topic, and then we will call it a day. And then from tomorrow, in the next class onwards, we'll take up the problem of radiation exchange between real surfaces and the radiation network. And then we'll also look into something which is known as radiation shield, and something which is known as two-zone enclosure, three-zone enclosure, and things like this in terms of radiation networks. Okay, so that's the agenda of how will we proceed in the coming classes. But today we will discuss into something which is known as radiation exchange between black bodies, and also we will see a glimpse of radiation network here, where I will show you how to draw the radiation network between two black bodies in picture. Okay, so I'll just formally lay out the problem here, and I believe the theory, of course, you have already seen it in the lecture series. So what I say is that, let's say I have a body which area is AI. Okay, and I have another body in space, let's say its area is, let's say, AJ. And now if I ask you what is the radiant energy, okay, that is leaving surface I and is intercepted by surface J, you can now straightforward say that it is AI times its radiosity Ji multiplied by, of course, Fij. That should be, because this AI being a diffuse body, it will emit, and of course it's a black body, so it will emit in all possible directions. So if you just want to calculate what is its amount that is being intercepted by this J, you need to multiply it with Fij, of course. Okay. Now, since it's a black body, I can always write that this Qi to J as AI times EBI, because for a black body, my radiosity is equal to the MSE power, and that becomes equals to EBI, since for a black body, I can always write my radiosity as nothing but my emissive power. Okay. All right. Now in the same sense, if I now define this QJI, that what is the radiant energy that is leaving now surface J that is intercepted by surface I can always write it as AJ times EBJ times FJI. Okay, this is my number two. That is trivial, right? Since this holds good from I to J, I can equally write this from J to I. All right. I hope this is clear to all. So now, when people talk about exchange, that we are basically dealing here, that we are not seeing just radiation as the radiation that is emitted from just one body. We are kind of looking into something which is known as radiation exchange. So when people say exchange, we need to look something which is known as the net radiation exchange taking place between these two bodies. Okay, or the net radiative flux in other words. So if I want to write the net radiation exchange between these black bodies, this is denoted as Qij. So if I just write Qij, I'm not meaning that it is transferring just from I to J or vice versa. It means it's the net radiation exchange. And this Qij, you can write in terms of these quantities, these individual quantities, as Q, you can write it as Qi to J minus Qj to I, and this signifies the exchange. And of course, if you write down their expression, it just becomes AI times what? Becomes AI times EBI times Fij minus Aj times Ebj times Fji. But since I know that my AIFij is equal to AJFji, that is from the view factor reciprocity, this is from the view factor reciprocity, of course, then I can write my, my net radiation exchange Qij as either AIFij times EBI minus EBJ or AJFji times EBI minus EBJ. The both are exactly the same. Why? Because of the view factor reciprocity relation. Okay, so you need to understand this. And if we just proceed with this form only, then I can just write this Qij, which is the net radiation exchange between the bodies I and J, as AI Fij. This EBI minus EBJ, if I use the Stephen-Boltzmann law, it can simply be written as sigma times TBI to the power 4 minus TBJ to the power 4. Okay, and this is not just true for only two bodies I and J. You can draw this conclusion for any generic bodies, for any two generic bodies. That's the thing that I want to portray. Okay, so this is precisely the net radiation exchange between two black bodies, I and J. And now what you can do is you can represent this Qij for black bodies as something like this: sigma times of TBI raised to the power 4 minus TBJ raised to the power 4 divided by 1 by AI Fij. And just how we saw that you can represent the net heat transfer as the temperature differences divided by the resistance. This can equally be termed as the radiation resistance, and this is known as resistance due to you know or this is known as this is sometimes known as the space resistance, to be precise. It's known as the space resistance between the bodies. And here it's the space resistance between the black bodies, which means that if I now have two temperature nodes, okay, Ti, and of course the second node Tj, I can now represent a resistance in between, okay, and this resistance is nothing but 1 by Ai Fij. That's it. Okay, and this is one way, and this is one such resistance. Okay, and this is one such resistance that arises in black bodies. In real bodies, there is one more resistance which is known as surface resistance, that arises typically because your radiosity and your emissive power is not the same in case of real bodies. And you have already seen that there is one more resistance. It is known as 1 minus epsilon I by Ai epsilon I, and this is known as surface resistance for real bodies. Surface resistance for real bodies. Okay, of course this term is not there if I have a black body in picture. Okay, so drawing the same analogy, if you want to draw the resistance network, okay, for real surfaces between two real surfaces I and J, you can just write it as Ti. There will be a surface resistance. This will be 1 minus epsilon I by Ai epsilon I. There will be a space resistance due to the fact that due to this fact that these two bodies are, so it's because like this will also emit in all possible directions and this will also emit in all possible directions, and that's why this space resistance that will come into the picture, which is nothing but this term 1 by Ai Fij. So it will just have 1 upon Ai Fij, and then we will also have one more surface resistance for the body J, because it's now the fact that it's not a black body, so it'll just have, so this is nothing, so people write it as Ebj, and this will be 1 minus epsilon J by Aj epsilon J. Now the thing is, people don't represent these nodes as temperature nodes, typically because your temperature has a 4th power. People represent this as, instead of representing this as temperature node, they represent this as emissive power nodes, and that's why they write these nodes as EBI, and this is nothing but EBJ. Okay, so you can represent that for a black body, the net radiation exchange is nothing but the difference between these emissive powers divided by the space resistance, which is 1 by AI Fij, because this can equally be written as what. So this sigma times of this is EBI, so this is EBI raised to the power 4 minus sorry, there won't be raised to the power 4 now, it's just EBI minus EBJ divided by the space resistance, which is 1 by AI Fij. Similarly, for real bodies, you can equally represent, similarly for real bodies, drawing the same analogy, this will be, this will be EBI, of course. So the net radiation exchange in terms of the resistance for real bodies, I will write it as Qij real. This will be nothing but your EBI minus EBJ divided by, now instead of just having one space resistance, you will have one space resistance and two surface resistance, typically because your bodies now are they are no longer black bodies, and they are now real bodies. So these node now becomes your radiosity nodes, as you have seen in your in your lecture classes. This becomes Ji, and this becomes your Jj. And if I have a black body, this typically becomes equal to this, and that's why you don't encounter these resistances in case of black bodies. But this is true in case of real bodies, so that's why this radiation network is for real surfaces. Okay, and this is for black bodies. Okay, so this means if I want to write Qij for a real surface, I will have the space resistance for surface I, which is 1 minus epsilon I by AI epsilon I. I have, sorry, this is the surface resistance for surface I. I have 1 by AI Fij plus 1 minus epsilon j by Aj epsilon j, and this is precisely my net radiation exchange between two real surfaces, where, as I said, these are the surface resistance. This is my surface resistance for I. This is my surface resistance for J, and of course this is the space resistance. Okay, so this is typically the radiation exchange, and this is typically how you write the radiation exchange network. So this is nothing but the radiation network that we drew. This one is for black body, this one is of course for real body, and this is the manner that we write the radiation, the net radiation exchange between two different bodies. This is of course for real bodies, and of course this is for is for a black body. Okay, so this is something to do with radiation exchange, and we stop here today. In the next class, we will look into a problem of involving this radiation network. We'll look into a problem. So of course, this we have already seen, radiation network, radiation exchange is real surfaces. This is exactly what we meant by that. Okay, and in the next class, we'll look into a problem that involves understanding these radiation exchanges in case of real surfaces. So I stop here today. Sorry. So if you have any questions, you can ask me, or else we will meet it in the next class. The next class, as you know, is again in the same time, that is from 3 to 5 on Saturdays. But I hope like today you got some crucial insights on the most important and the most fundamental concept of radiation exchange, that is known as the view factors, and that how to write the radiation exchange in case of the black bodies, and how to write the radiation exchange in case of real bodies in terms of the radiation network. And try to understand, we don't, in radiation network, we write the differences between the emissive powers, typically because this is related to the 4th power of its temperature. So in conduction, it was just the linear power of temperature, but here, since it's a 4th power of temperature, in case of writing delta T, we write the differences between their emissive powers in the radiation network analysis. Now, of course, you can always relate this to the temperature using the Stephen-Boltzmann law for black bodies. Okay, and for real bodies, we saw that the radiosities and there is a resistance actually for real bodies. There is a resistance in the surface itself, and that's why this resistance is known as surface resistance. Okay, there is a resistance in the surface itself that was no longer present in case of black bodies, but because it's a real body, due to its own emissivity, there is a resistance in the surface itself, and you can prove that this resistance, just by using the relationship between your radiosity, and the emissive power that we saw some classes back. You can prove that the surface resistance is indeed 1 minus epsilon I by AI epsilon I, where epsilon I is the emissivity of surface I, of course, that you guys know. Okay, so this epsilon, although I didn't write it here, but I think by now you guys know that this epsilon I is emissivity of surface I. And so is the case for epsilon j, which is the emissivity for surface j. So you can appreciate that in real surfaces, the surface itself adds a resistance which was not present in case of black bodies. In case of black bodies, we just had this space resistance, but in case of real bodies, in addition to this space resistance, we have these two surface resistances. Okay. So this is something that we saw. In the next class, we'll look into some good, numericals associated with this radiation exchange, and then we'll look into something which is known as enclosures, how to draw radiation exchange for 2-zone and 3-zone enclosures, and finally we'll see something which is known as radiation seals. Okay, and how to basically write the net radiation exchange in terms of course of course we'll use this form exclusively to write the net radiation exchange. However, now we'll extend this discussion into more complicated scenarios involving enclosures, for instance, 2-zone enclosure and 3-zone enclosure, and also radiation seals. Okay, this we'll see in the next week and the coming week after that. But till now, like, I hope everything up to this point is clear to you. Thank you for attending, and if you have any doubts, please post it in the discussion forum. I'll be happy to address. Thank you very much.